Hello guys, so previously in our last session we were looking at error detection and correction, specifically Hamming codes. So Hamming codes is a block code that is capable of detecting up to 2 simultaneous bit errors and correcting single bit errors. So it was developed by R.W. Hamming for error correction. So in Hamming code method, the source encodes the message by inserting redundant bits within the message. These redundant bits are extra bits that are generated and inserted at specific positions in the message itself to enable error detection and correction. So when the destination receives this message, it performs recalculations to detect errors and find the bit position that has the error. All that we saw in our previous session. So in this session, I would like to clarify some bits that we covered last time. So the Hamming code, we have the 7-bit Hamming code and we also have the 11-bit Hamming code, but the 7-bit is the most commonly used. So the 7-bit Hamming code, we have 7 bits, of which 3 of them are parity bits and 4 are data bits. P refers to the parity bit and D refers to the data bit. So according to Hamming code, the position of the parity bits is calculated using this table. So basically here we just have number 1 to 11 in decimal notation, and then written out in binary form. So as you can see, 1 is 001, 2 is 0010, 3 is 0011, and so on and so forth. So you would write the parity bits. So we have parity 1, parity 2, parity 4, and parity 8. They are in increments of the powers of 2. So we have 2 raised to power 0, 1, 2 raised to power 1, which gives you 2, and then 2 raised to power 2, which gives you 4, and 2 raised to power 3, which gives you 8. So these 1, 2, 4, and 8 are what you see as parity 1, parity 2, parity 4, and parity 8. So you draw this table 1 to 10 decimal, parity 1, 2, 4, and 8, and you write out the binary equivalents of the decimals 1 to 11. So the position of the binary 1 is what determines the position of the parity bits in the Hamming code. So as you can see, the binary equivalent of 1 is there. So for parity 1, where the binary 1 appears is the position of the parity bit in the Hamming code. So for parity 1, when you want to calculate parity 1, you will look at the data bit in position 3, position 5, position 7, position 9, and position 11, depending on whether you're using 7-bit or 11-bit. So for parity 1, you will look at D3, data bits 3, 5, and 7. Okay. For parity 2, you look at data bit 3, 6, 7. For 4, you will look at 4, 5, and 6. If you're using 11-bit, you will look at 8, 9, 10. As you can see, 8, 9, 10, and 11. So let's understand it better by looking at an example. So let's say we have a data stream of 1011. You write it out. We're using the 7-bit Hamming code, so you will draw 7 bits, and position the data bits. So if you have 1011, so this will be data bit 7, data bit 6, data bit 5, and this will be data bit 3. So parity bit 4 will be there, 2 and 1. Okay, so parity 1, parity 2, and parity 4, because we are using the 7 bit. So we are using even parity. Okay, so even parity, you will ensure that all the ones add up to an even value. So for parity 1, we said we are looking at data bit 3, 5, and 7. So data bit 3 is 1, 5 is 1, 7 is 1. Those are three ones, and we're using even parity. So to make it even, we'll have to add a 1. So that's why parity bit 1 is 1. Moving to 2. Okay, so in parity bit 2, we will look at data bit 3, 6, and 7. So 3 is 1, 6 is 0, 7 is 1. How many ones do we have there? We have 2 ones. So it means that there is an even number of ones. So when the number of ones is even, the parity becomes 0. Moving on to 4, we look at 4, 5, and 6. So 4, we look at data bit 5 and 6. Okay, so 5 and 6, we have 1 and 0. So to make it even, so for parity bit 4, we look at 5, 6, and 7. So 5, 6, and 7. So we have 2 ones, which is even. So the parity is 0. So if you insert the parity bits within the data bits to form the Hamming code, you will have 1, 0, 1, 0, 1, 0, 1. Okay, so inserting the parity, 4 was 0, 2 was 0, 1 was 1. So it gives you this Hamming code. Okay, so this is the code that will be transmitted, 10101001. So for example, we want to detect an error that has occurred during transmission. So if we say we'll take the example of our Hamming code, this is what has been transmitted, okay, and the received code is this. Yeah, so we want to detect the error. So we do this by finding the parity bits in the received code. If it is different from the transmitted code parity of 100 that we got in the beginning, then there is an error. So we will take the received code and label the positions of the parity and the data bits. So we will calculate the parity for the received code. So parity 1, we will look at 3, 5, and 7. So 1, 1, 1. So 3 ones, we add 1 to make it even, because we are using even parity. Parity 2, we will look at 3, 6, and 7. So 1, 1, 1. We still add another 1 to make it even. Parity 4, we will look at 5, 6, and 7. So it's also 3 ones, we add 1 to make it even. So we can see that the parity for the received code is 1, 1, 1. Okay, but for the transmitted code, the parity was 100. So we see it is different. It means that there is an error in the transmitted data. So we know now that there is an error. So how do we correct this error? How do you correct this error? Okay, so first we find the position of the error. The received code was 1, 10101. Okay, so we will still position it the way we did in the beginning. So from the received code, we will extract the following. So remember, we are using even parity, don't forget this. So this was the received code, yeah. So we want to detect where we've already known that there's an error, so we need to find the position of the error and correct it. Okay, so writing it out this way, we start with parity 4. Okay, so parity 4, we know it is given by 5, 6, and 7. Yeah, so 5, 6, and 7 are 1, 1, and 1. And in the received code, parity 4 was 0. So we want to calculate the new parity. So we'll count the number of ones. There are 3. Because we are using even parity, we have to add 1 to make it even. So parity 4 will become 1. We move to parity 2. Parity 2 in the received code 0. And the data bits we look at are 3, 6, and 7. So 3, 6, and 7 are 1, 1, and 1. And the parity 2 was 0. So counting the number of ones, it is 3. We add 1 to make it even, 4. Yeah. Parity 1 is 1. And we look at the data bits 3, 5, and 7. 3, 5, and 7 are also 1, 1, 1. So we have even number of ones, so P1 becomes 0. So the parity bits for the received code that we calculate using the received code, we found it is 1, 1, and 0. Okay, so this is in binary notation. In decimal notation, 110 becomes 6. Is 6. Yeah. So we go to the received code. The data bit in position 6 is where the error occurred. So looking at this, we have position 6, we have a 1. So this is where the error occurred. Since it's a 1, the correct bit will have been 0. Okay, so since the error is in position 6, the 1 changes to a 0. So the error has been corrected. Yeah, so it should be 1 in position 6. The error was a 1, so we change it to a 0. 1, 0, 1, 0, 1, 0, 1. So if you extract the data bits, the original data, you remember the original data stream we had was 1011. Yeah, and the Hamming code without error, the transmitted code was 101010. It was this one. So the received code was this. We detected the error in position 6, changed it to a 0. So we found the original code was back to that, which is this one. Okay, so that's how we use the Hamming code to detect and correct errors. Thank you.